Hello, my name is William Cranford, and I will be presenting Lab 3 for Physics 2212. Lab 3 focuses on the magnetic fields produced by a permanent dipole magnet. The goals of this experiment were to identify the distance dependence for the bar magnet I use by evaluating the magnet's effect on the magnetic field while positioned both on axis and off axis. We also had to calculate the net magnetic field caused by both the bar magnet and the Earth. And then we were asked to utilize the data from this experiment to determine the values for N, magnetic field, and the magnetic dipole moment. Overall, this lab helped us better understand and visualize the magnetic field produced by a bar magnet. Key principles applied to this lab include superposition, as we had to sum up the magnetic field produced by the bar magnet and the Earth in order to find the net magnetic field. We had to have an understanding on the effects of bar magnets when positioned both on axis and off axis. And finally, we had to apply the Biot-Savart law in the coding in order to model the magnetic field produced by the bar magnet. For this lab, we had to download a magnetometer app that would record the magnetic field in the X, Y, and Z direction. The next step was to compensate for magnetic north. I had to rotate my phone until the X component of my magnetometer app read close to 0. Then, my phone was positioned along the Earth's magnetic north-south axis. The next step in the lab setup was finding the magnetometer chip in my phone. I put my bar magnet at one end of the east-to-west oriented meter stick. I then moved my phone along a line perpendicular to the meter stick. I placed a piece of tape at the location where the X component of the magnetic field was at a maximum and the Y component was at a minimum. I then rotated my phone 90 degrees and repeated the process, but placed the tape where the Y component was at a maximum and the X component was at a minimum. The magnetometer chip was found to be at the intersection of these two tapes. For the first part of the lab, we were asked to measure and record distances from the magnet to the sensor that produce a magnetic field with an X component of magnitudes 20, 70, 120, 170, and 220 microteslas. I took 3 measurements for each of these magnetic field values. Some key observations I made while conducting this part of the lab was that when the magnetometer app is far away from the magnet, it measures a near zero magnetic field in the X direction. The position of the magnetometer has an effect on the measured X component of the magnetic field. And as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Here are the results I obtained from conducting this part of the lab. This data would then be used to plot a graph of ln of the X component of the magnetic field versus ln of the separation distance between the magnet and the sensor. Here's the plot. The equation for this line is the natural log of the X component of the magnetic field is equal to the natural log of the K constant plus the distance dependence times the natural log of the separation distance. As you can see, the slope of this line is equal to the distance dependence. In effect, I obtained a distance dependent value of negative 2.8867, which is close to the expected value of negative 3. In order to solve for mu, I evaluated the plot at the y-intercept. In this case, the natural log of the X component of the magnetic field is equal to the natural log of the K constant, which is equal to negative 13.96. Using simple algebra, I solved for the K constant, which was found to be 8.65 times 10 to the negative 7. Using the equation K constant is equal to mu naught over 4 pi times 2 mu, I was able to solve for mu. And I found mu to be 4.327 ampere meter squared. Here's the computational model produced by the code for Lab 3. Using the Biot-Savart law, this code calculates the magnetic field produced by a dipole. The blue arrow represents the magnetic field produced by a dipole on a perpendicular axis, and the orange arrow represents the magnetic field produced by a dipole on axis. The code was also written to compute a magnetic field along the 45-degree axis. This value will be compared to the value we obtained in Part 2 of the lab. Part 2 of the lab asks us to measure the off-axis field produced by a magnet. Using the same experiment setup to measure the on-axis field, I measured a distance d-perp for which the magnet produced a value of 100 microteslas for the X component of the magnetic field. The phone was then moved up a distance d-perp and the magnetic field components were recorded at this location. The Y component was corrected to account for the Earth's magnetic field. Here are the results from Part 2 of the lab. As you can see, the average distance measured is very similar to the distance computed by the computational model. However, the magnetic field found in Part 2 of the lab differed significantly from the magnetic field produced by the computational model. Moving on to the discussion questions, if I hadn't oriented my experiment to compensate for magnetic north, my results would be skewed. The Earth would now produce an S component of magnetic field, and we would no longer be able to isolate the effects of the bar magnet. If I were to stick 2 identical magnets together, the total magnetic field produced would be much stronger, which would lead to larger separation distances.